In this video, we solve problem 4.7.43 from Nagle's Fundamentals of Differential Equations, 7th edition. We're told that a differential equation and a non-trivial solution f are given. We're asked to find a second linearly independent solution using reduction of order. We're asked to assume that all constants of integration are 0. So we have this differential equation and this as our f of t. All right, now, one thing that I will say is that the method that I showed you in class is different from the method that the authors of the Nagle textbook and the authors of the MyLab Math course materials proceed through when they use reduction of order. But I will show you how to do it the way that we talked about in class, and then I'm not going to focus so much on their solution method, but I will show you how our solution is equivalent to the solution that they are looking for. Okay, so we want a second linearly independent solution. So if we have our first solution, I might call this like x sub 1 of t. The second solution, x sub 2 of t, if it's linearly independent, has to be given by u of t times x sub 1 of t. So let's let x sub 2 equal u times x sub 1, where u is a function of t and it's not a constant function. We don't want it to be constant because we want these two functions to be linearly independent from each other. So we're going to let x2 equal u times x1, which is u times e to the 2t, where u is not a constant and u is a function of t. And then we want to find that function u of t so that x2 is a solution. So in order to do that, since this is a second order differential equation, we'll compute the first and second derivative. Remember, u is a function of t. So when we compute the derivative of this, we have to use the product rule. According to the product rule, x sub 2 prime is derivative of the first times the second, plus the derivative of the second. Derivative of e to some power is e to that power times the derivative of the inside. And we're going to multiply that by the first function. Okay, so that's x sub 2 prime. X sub 2 double prime requires us to use the product rule again here and here. So this will be my first function and this will be my second function. And then on this one, this will be my first function and this will be my second function. According to the product rule, we have derivative of the first. So derivative of u prime is u double prime times the second, undifferentiated, plus the derivative of the second. Derivative of e to the 2t is e to the 2t times the derivative of the inside, which is 2, times the first, which is u prime, undifferentiated. That's just for this first piece. Okay, so that was that product rule. Now we have to do the product rule again over here. We want derivative of the first. We'll have 2 times the derivative of e to the 2t. That's e to the 2t times the derivative of the inside. That's an extra 2. That's derivative of the first, and we need to multiply it by the second function. And then we'll add the derivative of the second function times the first. And let's see if we have any like terms. I've got the first is actually 2e to the 2t. We've got 2e to the 2t times u prime there and 2e to the 2t times u prime there. So these are like terms. I've got 2 of them here and 2 of them there. That means I have 4 of them total. And then I have 4 times e to the 2t times u for that last term as well. Okay, now we will substitute x sub 2 prime, and x sub 2 double prime into this equation. Now we're assuming x sub 2 is a solution, so when we substitute, we should get 0. All right, that's the plan. Let's do it. So the original differential equation was t And then we're going to substitute in x sub 2 double prime minus the quantity 2t plus 1 times x prime. We're going to substitute in x sub 2 prime. And then we're going to add 2 times x sub 2. And if x sub 2 is a second linearly independent solution, we're going to get 0. So let's substitute. So we have t times x sub 2 double prime, which is that expression right there. And then we're subtracting 2t plus 1 times x sub 2 prime. Since x sub 2 prime has 2 terms, I think I'm going to distribute first. So this will be negative 2t times x sub 2 prime minus 1 times x sub 2 prime. We're going to add 2 times x sub 2 and set that equal to 0. Now, x sub 2 prime is this u prime e to the 2t plus 2 e to the 2t times u. And x sub 2 was just u times e to the 2t. Now, whenever you use reduction of order, we call it reduction of order because this is going to simplify to a first order linear equation in u prime. So it's actually going to be a first order equation rather than a second order equation after we make a substitution. So we're reducing the order from second order to first order. But that requires us to simplify first. So we'll have t times that expression plus t times that expression, and then t times that one. Distribute the 2t here. Distribute the negative there. And then you've got a positive there. Now, hopefully all of the u terms reduce. So that's what's necessary for this to be first order linear in u prime. I've got negative 2u times e to the 2t and positive 2u times e to the 2t. So those undo each other. Those are gone. Those operations undo each other. And then we've got one of these here. No, that's a u prime term. We've got one of these u terms, 4t times the exponential times u. And then we have a negative 4t times the exponential times u. So those undo each other. Those are gone. We're adding that and then we're subtracting that. So those are gone. And let's see, is there anything else? Anything else we can combine? Well, I don't have any u terms left. That's a good sign. I've got this t times e to the 2t times u double prime. And then I've got 4t times the exponential times u prime minus 2t times the exponential times u prime. So that's going to be 2t times the exponential times u prime minus the exponential times u prime equals 0. So maybe we should factor out that u prime there. And then maybe divide everything by this coefficient, t times e to the 2t. Oops. And of course, dividing 0 by something just leaves you with a 0. And if I factor out the e to the 2t there, I have this. So the e to the 2t's reduce, and we end up with this. If I divide each of those terms by t, I have 2 minus 1 over t times u prime. That's first order linear in u prime. So before we go on, let's see, we substituted x sub 2, x sub 2 prime, and x sub 2 double prime into the dE. Then we simplified. And now we're going to make a substitution. We're going to let w equal u prime. Then if we take the derivative of w, that's u prime prime, so u double prime. Then we want to write this as a first order linear equation in w. So our new differential equation is u double prime, which is w prime, plus 2 minus 1 over t times u prime, which is w, and that equals 0. Now this time, the differential equation happens to be separable. So if you want, you could just solve this by separating the variables, and that would be totally fine. I think that's what I'll do this time, rather than using an integrating factor here. Now, in general, this will be first order linear, and it is first order linear, so we could solve with an integrating factor, but this time I think it's going to be easier to use, or since it's separable, it would be easier to solve it by separating the variables. So let's solve the separable equation. It's going to allow us to find w. That requires remembering that dw, or w prime, is the same as dw dt. We'll subtract this from both sides. So it's just going to flip the signs and put that over there. Now, if we multiply both sides by dt and divide by dw, we'll have 1 over w times dw equals all of this times dt. And then we'll anti-differentiate both sides. We've separated the variables by dividing by w and then multiplying by dt. Okay. And now we anti-differentiate. Okay. This side is natural log of the absolute value of w. This side gives us a negative 2t plus natural log of the absolute value of t plus a constant of integration. And if we want to get w by itself, we would raise both sides, or use both sides as the exponent for an exponential function. So this over here will give us the absolute value of w. And this is the same as this. We've got, like, if we had x to some power times x to a different power, we would add the exponents. So if this base is an e rather than an x, it still holds. We've got a sum of exponents here. So we actually can write this as a product. We can write this as e to the negative 2t times e to the natural log of the absolute value of t times e to the c. And that absolute value of w just means we're going to have a plus or minus there. So we've got plus or minus e to the c times this, and these guys will undo each other, so we'll end up with an absolute value of t. Now, we were told at the very beginning that t is greater than 0, so the absolute value of t is just t, and this is just a constant. Okay, so that's our w. Keep going. Now remember, w is something that we made up so that we could solve this problem. So we want to go back to u. So we have to replace w with u prime. So we have u prime is equal to a constant times e to the negative 2t times t. I forgot to write down. We anti-differentiated both sides, and then we just did some algebra to solve for w. Okay, now we're here. So we back substituted. We replaced w with u prime. All right. And if this is u prime, that means u is the antiderivative of u prime. So we'll use integration by parts. Since I've got a polynomial times an exponential, I'm going to use tabular integration. That's my u and that's my dv. Of course, this u is different from that u. So I've got a constant times t there, and dv is e to the negative 2t times dt. The way this works is you differentiate until you get 0 in this column. Derivative of a constant times t is the constant. And then you anti-differentiate in this column until you have the same number of rows in both columns. And then we multiply across this diagonal, and then we add, and we multiply across this diagonal and multiply by -1, and then we add. And then we would have a constant of integration as well. So we'll have this times this is going to give me a negative c1 times t over 2 times our exponential, minus c1 over 4 times the exponential, plus a constant of integration, a different one. So that's our u, and x2 is u times x1. So x sub 2 is this function times x1, and x1 was e to the 2t. Now, we are already going to have a constant times e to the 2t in our general solution. So usually we choose this constant of integration to be 0, because we don't need a constant times the first solution as a part of our second solution. And we're going to take x2 and multiply it by an arbitrary constant. So we can choose c1 to be any value we want, and then that would still work. So if I choose c2 to be 0, and I choose c1 to be, let's say, 4, I could clear all the fractions. Or I might even choose c1 to be -4 to make this nice and clean. Then x2 is going to be -4 divided by -2, which is positive 2t times this exponential. And -4 divided by -4 is just going to be 1 times the exponential. And we're multiplying that by e to the 2t. So it's going to give us 2t plus 1 as our x sub 2. That's what I would prefer you do. And then the general solution from there, even though they didn't ask for it this time, would be c1 x1 plus c2 x2. Or in other words, c1 times e to the 2t plus c2 times this 2t plus 1. That's one way of doing it. Now, the answer that they are expecting you to get comes from what they said at the very beginning. They wanted us to assume that all constants of integration were 0. So when we went through our method, and we were right here, they wanted us to assume that that c equals 0. If that c is 0, then that means this e to the c is equal to e to the 0, which is 1. And so we'd have plus or minus 1 times this for our w. And they're actually ignoring the plus or minus here. So they're just going to have c1 equals 1. And if c1 equals 1, rather than getting this solution, which comes from setting c1 equal to 4, we would get -1/2 t x of t, or x of 2 would be -1/2 times t times e to the -2t minus 1/4 times e to the -2t. That's our u times this exponential. And then when you distribute, you get this. Now, you might say to yourself, how do I know to do that? It's just because of what they said. They said they wanted us to make all constants of integration equal to 0. And then they're sort of ignoring that plus or minus over here. If we let that constant of integration equal 0 and we let that constant of integration equal 0, then we would end up with right here. This would be 0, and that would be a -1/2, and that would be a -1/4. But notice if I multiply this by -4, I get this solution. And that's equivalent because this function and this function are linearly independent from each other. So the general solution will be a constant times e to the 2t plus a constant times this function. And one version of a constant times this function is a constant times this function, because this function and this function are linearly dependent. This function is just -4 times that function. I like to write it this way because I like to clear the fractions when I can. But if you don't clear the fractions, you'll get the answer that MyLab Math is expecting you to get. So let's go through the method of reduction of order just one more time. If I know a second solution and I have a differential equation like this, I know one linearly independent solution of a second order equation, then the second solution has to be u times the first solution, where u is not a constant, because if it were a constant, these would be linearly dependent functions, and we want them to be linearly independent. So you say, okay, there's got to be a function out there, u, which is a function of t, so that this satisfies this equation. What does u have to be? Well, in order to figure out what u is, you take the first and second derivative, you substitute into the equation. After you do that, and after you simplify, every time you're going to end up with a first order linear differential equation in u prime. All the u's should cancel. And if you let w equal u prime, you're going to have a first order linear equation in w. Now, you can solve that equation. If it's separable, like this one was, you can solve it by separating the variables. If it's not separable, you can solve it using an integrating factor, but you're going to solve it. After you solve it, after you get that w, then you have to remember we're trying to get x sub 2. And x sub 2 is u times x sub 1. So we need to get from w back to u. So we have to back substitute. W is actually u prime. So we replace w with u prime. And we say the derivative of u is this. Well, then u must be the antiderivative of that. So we compute the antiderivative. And if we let this constant of integration be 0, we get this. And if we let this first constant, or if we let this first constant of integration from our solving the separable equation be 0, these C1s turn out to be 1. Actually, they turn out to be plus or minus 1. And that gets you this answer here. I like to choose C1 to clear the fractions. So I would have chosen C1 to be -4 to make that sort of nicer, prettier x sub 2. But this x sub 2 and this x sub 2 are equivalent to each other in the sense that these two functions form a linearly independent set of solutions to the differential equations or to the differential equation in this problem. And this function combined with this function form a linearly independent set of solutions. So when we take them and we multiply them by constants and add them together, we're getting basically the same thing in a slightly different form. So that's it. We replaced the w with u prime. We anti-differentiate u prime to get u. Then we say that x sub 2 is equal to u times x sub 1, or the second solution is equal to u times the first solution. And then you weren't asked for the general solution, but the general solution is C1 times the first solution plus C2 times the second solution.